let me remind you. So first of all, I gave a definition. So that if we have a square matrix and rows and columns, then A11, A22, A33, ANN. So these things comprise a main diagonal. So identity matrix denoted as I is the matrix which has ones on the main diagonal and zeros everywhere else. So just by mechanics of multiplication, identity matrix multiplied by any vector will leave the vector unchanged, right? Any questions or not? Do you have any questions?
I have one.
Yes, go ahead.
Are all identity matrices square? Like in order to be an
yes.
Okay.
Because as I said, so it's defined through having ones on the main diagonal, right?
Right.
But I mean, you cannot introduce main diagonal for any matrix but n by n matrix, right?
Right. Okay.
So essentially zeros everywhere else but ones on the main diagonal, right? Okay. So from here, from this statement, just from mechanics of multiplication of identity matrix on any vector, you can immediately understand that also identity matrix n by n or m by m identity matrix multiplied by any m by n matrix gives me original matrix itself, right? Because I told you that the multiplication of a matrix on another matrix you can consider as multiplication of this matrix on every column of the matrix A, right? But because identity matrix doesn't change this column, so you will get the same matrix. Now, another thing is interesting. So we discussed that every map, every linear map has a representation as a matrix, right? And vice versa, every matrix represents a map, right? So if you consider this vector, column vector, as coordinates vector with respect to some basis, right? Then identity map, because it doesn't change the vector, identity matrix, sorry, because it doesn't change the vector, nothing is nothing else but matrix representation of an identity map, right? Which leaves all the vectors the same. Okay, if you're talking about n by n, it's a matrix representation of an identity map for n-dimensional space. Pay attention that it doesn't matter what basis you will choose, right? So if you start in this start and end in the same basis, so identity map doesn't change the vector, right? Is it clear or not? Because coordinates are the same, right? So for example, let us consider this, right? So if you consider x1, x2, have a look. what you will get? You will get x1 plus 0x2, right? 0x1 plus 1x2, right? So exactly x1, x2. So, and the idea is that for 3 by 3 identity map, for example, identity matrix, so have a look, just by mechanics, because you are multiplying these on that, so the first line will cut only the first coordinate. The second line will cut the second coordinate. The third line will cut the third coordinate. So as a result, you will get the same vector. Okay, now definition. A diagonal matrix is square and has 0 entries of the main diagonal. So in other words, here I would have everything else 0, right? And then this would be diagonal matrix. A little bit later, we will talk about what a linear map with a diagonal matrix does with the vector. So really, you can see it even now. For example, let us consider just x1, x2, and so on, xn, right? The usual vector belonging to Rn. And here we have a diagonal matrix. Then the result will be this. And what it does with the vector. So essentially, you can see it as the following. So let us have a look. So if we started from the vector x, right? So what will happen with the length of the vector after multiplication by diagonal matrix? Okay, so let me call this D. D, and this vector x. So let us have a look what will happen with that. So the length is in Euclidean space, so it's a1 square x1 square, sum of the squares of the components, right? And then you need to compute the square root. So you see what happens. Even the length, so the length of the vector will change, right? So you can easily see that the direction will change, but also the length of the vector will change as well. So, okay, we will talk in a little bit more details later. So what linear map with corresponding diagonal matrix does with the length of the vector and so on. So I just don't want to go into details here. Okay, now also let me introduce definition. A permutation matrix is square and is all zeros except for a single one in each column and row. So definition looks strange, but let me remind you, I told you how to get matrix representation of elementary row operations. So I told it to you before. So idea is the following. So let us suppose that you know the operation, you're trying to find matrix representation of an operation, elementary row operation, which it does on the on your corresponding matrix. So here is your matrix A, right? For example, you want to exchange two rows, any two rows, right? So how can you write it? You can write it as elementary row operation. So just matrix, which you don't know. Then you can write it as identity matrix. And then your matrix A. Because as I told you, identity matrix doesn't change the matrix, right? So you can just always write your matrix A as identity matrix multiplied on A. Okay. Now we had it already that we can put the brackets in any way, right? So here we said that we have it like that. Now I'm saying that because matrix multiplication has this property, so I can change the position of the brackets. And then have a look. This matrix is the same elementary row operation over identity matrix. So now you know how to find elementary matrix representation of any elementary row operations. So for example, let us consider 3x3 system. And we want to exchange row 1 and row 3. Then we have to perform exactly the same operation over identity matrix. So it's 0, 0, 1, 0, 1. This stays the same, second row, and the first row becomes the third row. Is it clear or not?
It's clear.
Yes.
So what we end up with is the permutation matrix?
Yeah, matrix representation of elementary row operation exchanging row 1 and 3, right? Yes, and this is exactly what I'm trying to say. So any permutation matrix thank you for reminding me. Probably I would forget about it. So any permutation matrix is can be obtained from identity matrix, which is also permutation matrix, right? So but what is interesting, because it has one non-zero element, which is 1 in every column and row, right? And then now, if you exchange them, so for example, let us get the let us exchange the first two rows. So we will get 0, 1, 0, 1, 0, 0, 0, 0, 1, right? So this is elementary row operation, R1 exchange with row 1 exchange with row 2, right? What is interesting, that exactly the same approach can be applied not necessarily to elementary row operations, right? We know there are only 3 of them, right? Exchange of rows, multiplication of a row by non-zero number, and replacement of a row with a sum of the same row and multiple of another row. But for example, if you want to exchange 2 columns of a matrix, so you need to perform exactly the same operation over identity matrix, and you will get exactly, for example, let me exchange first. So I start from here, right? Identity matrix. And I want to exchange column 1 and column 3. Right? So this is my matrix representation of this operation. Okay, so now if I want to multiply, for example, by alpha, non-zero alpha, I want to multiply row 1. Yeah. So again, starting from identity matrix, and this is what I will get, right? Oops. Right? Is it clear or not?
I think I'm a little bit confused as to why you can perform a scalar operation to like just one of the rows. Like I know you can do that in elementary row operations.
No. Yes, I'm saying that if you want to find matrix representation of any operation over the matrix, just perform exactly the same operation over identity matrix. Have a look. So M on A, right? This is the matrix representation of some elementary row, not necessarily, just any matrix operation. So I can write this like that because identity matrix doesn't change the matrix. And then I can use just exchange the brackets, right? So I can write it like that. And then essentially I know that this will be nothing else but matrix representation of an operation. So if I wanted, for example, to multiply some row by the scalar, so I have to perform exactly the same over identity matrix. I need to multiply, in this particular case, the first row by the scalar. If I would need to multiply the third row by the scalar, so matrix representation would be, so I would have alpha here, right?
I'm starting to understand that, but what would M look like? Like you're just kind of showing.
I don't know. I don't know. This is exactly the thing. So I don't know how M will look like, but I know what it does. Now, in order to find how M will look like, so this shows that what I need to do, I need to perform exactly the same action over identity matrix. And this will give me matrix representation for any operation over matrices.
Okay.
So for example, you remember, we have this elementary row iteration, for example. Let's say I want to replace the third row with the sum of the third row. Yeah, let me just write. So we start from identity matrix, right? Not necessarily 3 by 3, of course, you can do it over any. So I want to replace row 3 with the sum of row 3 plus row 1 multiplied by 5. Right? It's elementary row operation. Right? I'm reassigning row 3, replacing row 3 with the sum of the row 3 and row 1 multiplied by 5. Because I'm changing only row 3, it stays this first and second row stays the same. But now I need to perform exactly this operation over the row 3. So it will be 5, 0, 1, right? So once again, I don't know in advance how it will look like, but I want to have a method which allows me to find the operation. So for example, if I multiply this on 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So if I multiply this matrix on that, this is what I will get. Have a look. First row stays the same, right? Because you multiply this on this, and that, right? Second row, second row stays the same. But when I multiply these on the first column, you see what I'm getting. I'm getting 7 plus 5, right? Multiplied on 1. Here I will get 8 plus 5 multiplied on 2. And the last one will be 9 plus 5 multiplied on 3, right? So exactly this operation. Once again, it doesn't matter what operation you are doing, not necessarily elementary row operation. For example, if I want to find the matrix representation of the following. So row 2 will be replaced with 6 row 3 plus 7 row 1, right? I don't know in advance what it will be, but because of these, so I have shown it to you, right? Or you can say these, you can just perform exactly the same operation over identity matrix. Pay attention, this is not an elementary row operation anymore, right? Because elementary row operation is replacement of a row with the sum of the same row, so the same, right? And multiple of another row. So, but here we are replacing the second row with the sum of the third row and multiple of another. Okay, let us do this. So first row stays the same, third row stays the same. We are replacing only the second row, right? So the second row will be row 3 multiplied by 6 plus row 1 multiplied by 7. So it will be 7, 0, 6. Just this. Is it clear or not?
I understand like how we do it, but I don't understand why.
I just want to find an operation, the matrix representation of an operation over matrix. So have a look. For example, I have a matrix A, right? I just want to find a matrix M such that if I multiply this matrix M on a matrix A, result will be exactly this matrix operation, right? So for example, replacement of rows or exchange of rows or multiplication of row by the scalar or whatever. So I don't know how this matrix M looks like originally, but what I can do, I can write that A is the same as M multiplied, the same as identity matrix multiplied on A. Now, using the properties of matrix multiplication, I'm just changing the brackets. What does it mean? What this bracket means? It means that first I need to multiply this M on my identity matrix, right? But I know what M does, right? So as a result, I know that M multiplied on the identity matrix will be exactly this matrix operation, for which I'm trying to find matrix representation. From the other point of view, I know that any matrix multiplied on identity will be the same matrix, right? So I found the way how to find matrix representation of any matrix row or column operation. I just perform exactly the same operation over identity matrix, which is simple, and this will give me matrix representation of this operation. Is it clear or not? No.
So,
Yeah.
oh, sorry, go ahead.
No, you go ahead.
Oh, okay. So, you don't know how the matrix M look like, but and it used the matrix M to represent the algorithm. For example, in this case, you represent R3 to R3 plus 5R1. Okay.
Yeah, you see, I'm trying to find this matrix M, right? So this just shows you how to do this. So for example, I will ask you to find the matrix representation. Yeah. Okay. We will talk about it right now. So, for example, you are performing. So you start from the matrix A, right? Which is just a matrix, right? M by N. Some coefficients matrix of some system of linear equations, right? And then after the series of operations, right? You are getting your matrix into upper triangular form. So MN. Let us start from square matrices. Doesn't matter really. It's simpler. N. And then you have something here, 0 here, 0, 0, 0. Everywhere here you have zeros. So this is called upper triangular form, right? So you can do this using elementary row operations, because this is essentially bringing your matrix to the, doing Gaussian elimination, right? Not yet Gauss-Jordan reduction, but Gaussian elimination, right? Is it clear or not? Okay, what is not clear? Could you tell me? So what I'm starting from, for example, matrix, right, like that, coefficients matrix like that. Can you tell me how to bring it to the row echelon form?
Subtract 2 times row 1 from row 2 and subtract row 1 from row 3.
Okay, let us do this. Let us do this. So what I will get here, I will get 0, right? 1 minus 3, right? Okay, so next, what I need to do next?
Subtract row 1 from row 3.
Just subtract, okay. 0, 0, 2, right? Right?
Right.
Okay. Could you tell me what will be representation of this operation? The first one.
Yeah.
I need to perform it, so just to make it simpler, I will write you identity matrix, right? So how can I do this?
R2 minus 2R1.
Just tell me. So first of all, this and that stays the same, right? Because I'm working only with R2, right?
Right, okay. So you would get 0 minus 2, so negative 2 for the first one. 1 minus 0 and 0 minus 0.
That's it, right?
Right.
Okay.
Could
So
you kind of explain that a little bit more?
So this is matrix A, right?
Yes.
I can write this as A multiplied on E1, performing first operation, and then multiplied on E2, performing second operation, right? Because I used first operation and second operation, right?
Oh, so you're representing these operations as two different matrices, not the same one.
Yes. I mean,
Oh,
I can,
okay.
but wait a little bit. So, okay, could you tell me what will be the matrix representation of the second row operation, this one? Just
the first row would stay the same.
Okay. Second two, right? Because we are working only with the third row, right?
Yes, the third row. So then it would be subtract row 1 from negative 1.
And
0,
everything else stays the same,
1.
right? Because of this 0, so everything else stays the same automatically, right? So,
okay.
So this is E2, right?
Yes.
Okay, you see. Oh, sorry. Yeah. So I can call this U, right? Upper triangular matrix. And these are lower triangular matrices. Because you have elements, non-zero elements only below the main diagonal, right? Or you can even say that this is unit, because lower triangular matrices, because you have ones on the main diagonal. Okay, now what I can do, I can say that I can combine these together if you like, right? Just multiply these matrices E1 and E2 in the right order, and then I will get nothing else but what? So 1, 1, 1, -2, -1, 0, 0, 0, 0, right? So I got some matrix, right? Which applied to my matrix A will bring it to the row echelon form, right? Is it clear or not?
How did you know how to get them like E1 and E2? So for one, you multiplied by 2 and subtracted, but for the other, you just subtracted?
Yes, because as I said, in order to find matrix representation of any elementary row operation, all you need to do just perform this same elementary row operation over identity matrix, right?
Oh, that makes sense. Yeah.
Okay. So what it means? It means the following, that I can formulate the following statement, that for any matrix H, or any matrix A, there are matrices representing elementary row operations. They are also called elementary reduction matrices, such that A, E1, okay, matrices EIs, E1, first elementary row operation, E2, second elementary row operation, E3, and so on till ER, such that is the result of this application is in row echelon form or even reduced row echelon form, right? Because I can, how to get a reduced row echelon form? You just continue performing operations. Reduced, if necessary, row echelon form, right? Is it clear or not? Yes or no?
Yeah, it's clear.
Okay, so if it's not, please ask me right now, because we will use it. Okay, now I want to introduce an interesting thing, which is called inverse matrix. So I essentially can introduce inverse matrix in the following way. Definition. A matrix G is a left inverse matrix, or just left inverse of the matrix H H, so left inverse of the matrix H, if GH is the identity matrix. It is right inverse if each G is the identity. A matrix H with a two-sided inverse is an invertible matrix. So the two-sided inverse is denoted H inverse. I mean, for matrix H. For matrix A, it will be A inverse. So idea is different, that A inverse on A is identity matrix, and A on A inverse is the identity matrix, because two-sided inverse. So now, how we introduce, so where the concept of inverse matrix is coming from. For example, you can do it like that. So have a look. Let us start from XYZ vector, right? In three-dimensional, let's say R3. So, and we perform projection on XY plane. So this is R2 already, right? So we start from three-dimensional vector and project it onto a two-dimensional plane. But also we can perform inverse operation, but it will not be complete inverse, which I will call I, which will be producing XY0. Y0, so it will be full inverse operation for the case if Z is equal to 0, then I is an inverse map for projection, right? Because then you will reconstruct exactly the same the original vector, right? Have a look. But also you can say like that. So if you start from the vector x, y, so you map with in inverse I on x, y, 0, and then projection will, projection will produce exactly the original matrix, original vector. So you can say that composition of I and projection is the identity map, right? On R2. Yes.
I had a question. Does it matter if you write I first or pi first?
Yes, it matters. It matters because have a look. If I so when I apply I, right here, I'm getting three-dimensional vector, right? And my projection operator is defined for three-dimensional vector, right?
Right.
So here I need first to apply I and then apply pi, right? Otherwise, if I first apply, for example, pi, I'm getting two-dimensional vectors, and then, yeah, so, okay, it's not exactly the same. This is why. Let me do this. So, for example, if I first apply pi, I'm getting xy, right? And now I apply I, right? So, and then I'm getting xy 0, right? So if z is equal to 0, then pi I, combination of pi and I is identity. So on a set of vectors xy, xy0, or you can say subspace of R3, right? There I will get identity map. But if I, for example, apply this to this, so pi 0, 0, so it's not the same as the original vector, right? Right or not?
Right.
Okay, now, could you tell me what will be the matrix representation? So you see, what will be if I'm considering just the natural basis, right? So how to get, so what will be the matrix representation to get x and y? So first of all, this is 3 by 1, right? And this is 2 by 1, right? So obviously this will be 2 by 3 matrix, right? All you need to do, you need to apply this projection operation to all the vectors of the natural basis, right? Natural basis is this, right? Anybody tell me what I will get as a result?
1, 0, 0 in the first row.
But let us do this column by column because we need to reply so our columns will be results of application of the map, right, to the vectors of the basis. So first column will be what?
1, 0.
Okay, second.
0, 1,
Thank you. And the third?
0, 0.
Thank you very much. Yes, so this is matrix representation of pi, right? Now, if I want to perform these, so I'm starting from x, y, right? 2 by 1, and I'm ending with 3 by 1. So it means that I know that this, in order to be compatible, this matrix has to have 2 columns, right? But 3 rows. Could you tell me what it will be? Once again, let us use the standard basis. Could you tell me what it will be? I mean, just map these using these. Anybody?
Would it be then by column 1, 0, 0,
Okay, and the second?
0, 1, 0?
Exactly. I mean, why am I so scary even when I'm teaching, I mean, using Zoom? So I will not do anything bad, so, right? So this is our matrix representation of I map, right? This map, right? Okay. Now, have a look. This is what happens. So if I will try to consider these, right? First I, then pi, right? So I need to multiply these. And here is pi representation 1, 0, 0, 0, 1, 0, right? So result will be, could you tell me the result?
A
I mean,
2 by 2 matrix.
Yes. So this is 3 by 2, 2 by 3. Result, of course, 2 by 2 matrix. Okay. Just multiply, please. So is it so hard?
The first element would be 1, correct?
Right. Next one.
0.
This on that.
On the row,
0.
yeah, 0.
And this one
0.
on the first 0, and
1.
on the second 1, which is 2 by 2 identity matrix, right? So which is not surprising, because have a look. Here we have identity map, right? So it means that this is left inverse for this matrix, right?
Yeah.
By definition. Or you can say that this is the right inverse for this matrix, right? Because this multiplied on that from the right gives you identity matrix. Is it clear or not?
Clear.
Okay, but if we change the order of multiplication, have a look. So which means I first apply, so this, first apply pi, which is 1, 0, 0, 0, 1, 0. And then I apply I. So result obviously will be, because this is 3 by 2, 2 by 3, the result will be 3 by 3 matrix, which is 1, 1. And then here, unfortunately, it will be this on that, right? 0. Everything else will be zeros. So this is not 3 by 3 identity matrix, because here we have zeros is instead of 1, right?
Yeah, correct. Yeah.
Yeah. So, okay, here you can see that we considered left inverse, right inverse, right? So, but we see that there is no complete inversion if we exchange the order, right, here. Because this will be inverse only on a subspace, some subspace of R3, right? This will be inverse map, right? Only for the subspace of R3. Is it clear or not?
That's clear.
Mm-hmm. Okay. Now, I can say the following. So let me formulate a lemma. If a matrix has both left and right inverse, then the two are equal. And these I don't need to prove, because it's just essentially correspondence between linear maps and matrices. So because just imagine that you have matrix A and B, right? And let us say that this B is A inverse. So A inverse is equal to identity matrix, right? So now, if I have also, so it's right. Okay, let us suppose that I also have left inverse. Identity matrix, right? So then from here, what I can do, I can just following what I'm doing. So here, this is if A correspond to some H, right? Then these correspond to H inverse, right? Because we are getting identity map, right? Here. So first of all, dimensions has to be the same, right? Because otherwise there is no, we need to have the same dimension if we have left inverse and right inverse. So, and here we have exactly the same situation, because we are using, essentially applying the inverse map to H, because we are getting the identity operator. Okay, now let me formulate also a theorem. A matrix is invertible if and only if it is non-singular. Let me remind you, what does it mean that matrix is non-singular? It first of all, it's defined only for square matrices, right? So matrix is non-singular if and only if. So we have a statement. The only solution for the corresponding system of linear equations, homogeneous system of linear equations, is the zero vector, right? Or in other words, if your reduced row echelon form will be just identity matrix like that, right? So it's easy to understand from the following. So let us consider, also we have proven that if we consider this, okay, B, let me call this B. So we have proven that if this is non-singular, then this always has solution and unique, and this solution is unique. Why? Because if the reduced row echelon form is this, right, then you immediately know that solution exists and unique, that first of all, because you will get just x1 equals to something, x2 equals to something, and so on, and there are no free variables, right? Okay, next. But if this works for any matrix X, vector X, right? So and for any B, so that for any B you can find such X that AX will be B. So it means that there exists well-defined inverse function, right? So essentially, you can say that this is a map, X map, mapped by AX, and this is B. And for any B, you have X such that it will be, if you will use this map, so you will get the corresponding B, right? So it means that you have onto, right? And because it's unique, solution is unique, so such X is the only one, then you have one-to-one, not just unique, but one-to-one correspondence. So it means that A represents isomorphism, and then correspondingly you can invert it. You can find A inverse such that if you will apply it to B, you will get an X, right? Okay, next, lemma. A product of invertible matrices is invertible. In other words, if G and H are invertible, and G and GH is defined, means that their sizes are compatible. Defined. Then GH is invertible and GH inverse is H inverse, G inverse. Okay, how to prove it? I mean, there are different methods of the proof. So, but because we came to the inverse matrix from the idea of inverse map, so such map that gives us in composition with the original map, so gives us identity map, right? So then we can say the following. So for example, we start from V, right, with respect to the basis B. And here we have H with corresponding matrix representation H, right? And here we have W with respect to basis C. So it's essentially BC, right? Okay, and then we have inverse map. And then correspondingly here we have inverse H. And here we have B with respect to V with respect to the basis B. So obviously composition H and then H inverse by definition will give us just identity map like that. So this is identity map, and we know that this identity map with respect to the basis B and B will be nothing else but identity matrix. So in other words, we have these, right? Now, let us consider in the same way G and H such that they will be mapping Rn, for example, to Rn. Doesn't matter any n-dimensional basis, any n-dimensional vector spaces, it's not important. And G would be a representation of really, no, let me just write it like that. So now, okay, we have G on H. So I first have V and I apply map G. I'm getting to, let's say, W, and then I apply map H with the corresponding matrix representation H capital, and I'm getting to Z, to vector space Z. So have a look. The combined map like that will have a matrix representation. So if we start from vector V here, what we need to do, we need first to map it using H, right? Sorry, G. G, and then H. So we have G, H, like that, right? Now, if I want to conceive, so, and let us say that all this is invertible. So essentially, I'm trying to find HG inverse, right? Matrix representation of the inverse map, right? HG inverse map. So then what I need to do, if I start from the vector Z here, right? First, I need to apply H inverse, which has corresponding H inverse. So from Z, I need to apply H inverse first. And then here, I need to apply G inverse with corresponding G inverse representation. Like that. So if I use some representation of Z with respect to some basis, so then I need first to multiply by H inverse, right? And then the result has to be multiplied by G inverse. So I'm getting HG inverse is G inverse, H inverse. Like that, right? Is it clear or not? Any questions?
No, that seems pretty clear.
Okay. Then let me formulate the last lemma for today. A matrix H is invertible if and only if it can be written as the product of elementary reduction matrices. Or representations of elementary row operations. We can compute the inverse by applying to the identity matrix the identity matrix the same row steps, the same elementary row iterations in the same order as for Gauss-Jordan reduction of our matrix H. Okay, sorry, I will just write the proof, which is extremely simple. So essentially, you start from H and you use E1, E2 series of elementary row iterations, right? So first of all, if I'm talking about invertible, it means that this is n by n square matrix, right? So you're getting what is, so you're essentially performing and you're getting identity matrix. Why it's identity? Because have a look, we have that if the matrix is invertible, then it is non-singular. But for non-singular matrix, reduced row echelon form
Did the audio cut out for anyone else?
Yeah, I don't hear him.
Yeah, same here.
It might come back in a minute.
Are you still here?
Yes.
Yeah, then we can hear you now.
Yeah, thank you. So it's just something happened with the iPad. Sorry. Okay, you can see the screen. Okay, so yeah, I stopped here. So you can write it like that because for non-singular matrix, elementary row, reduced row echelon form is identity matrix. But then what it means that so matrix is invertible if and only if it can be written as the product of elementary reduction matrices. Have a look. But then this is nothing else but H inverse, right? So inverse H equals to I, and vice versa. You can say that you can invert essentially. You can say that ER E2 E1. So applied on H equals to I, right? But then you can always add here identity matrix because it doesn't change anything. And then this is nothing else but H inverse. So it means that you can get H inverse as identity matrix, and then you apply to it just exactly the same elementary row operations, right? So, okay, it gives you a very powerful way of finding your inverse matrix. You just start, so if this is n by n matrix, you just start from augmented matrix such that here you have your matrix and here you have identity matrix, n by n. And then when you will transform this using elementary row operations, just perform Gauss-Jordan reduction. Gauss-Jordan reduction. You will get here identity matrix because it's non-singular. So then here automatically you will get the inverse matrix because then you will be performing exactly the same elementary row operations in the same order over the identity matrix. Is it clear or not?
It's clear.
Okay, thank you very much. Sorry for this delay, but now you're, I believe you are ready to finish, to do this last part in the homework. Yes, please, if you, I mean, I don't have enough time, but on the page 250, they go through the couple of examples of finding the inverse matrices using exactly this approach.